Okay, this video is going to look at the ideal gas law, Dalton's law of partial pressures, and Graham's law of effusion. The ideal gas law is up here on the screen. You can see that it's PV is equal to nRT, and the breakdown is over here on the right. We should already be familiar with P for pressure, V for volume, and T for temperature. The new additions to this one are N and R. N is the number of moles, and the capital R stands for the ideal gas constant. The nice thing about constants is that they're given to us, and we usually don't have to memorize those. We can look at them on a reference table. And if you're in my classes, I have given this to you already on this reference table. It has the gas constants right here. There are 3 of them. I'm going to talk in just a minute about how do you know which one of them to pick. Just to make them a little bit larger for our reference, I have written them down here on the bottom, and I've given you how to choose. If you can tell by looking at them, obviously all of the numbers are different. That's an obvious thing. None of them are exactly the same, but they are all the same in terms of the units. And yes, these are the units of the gas constant. It's all liters times some unit of pressure over moles times Kelvin. So the only thing that's different about all of them is the unit of pressure. This one's in atmospheres, millimeters of mercury, and kilopascals. So how you choose, I put right over here, you choose based on which one you have in your problem. If your problem gives you millimeters of mercury, then you would want this one. If your problem uses atmospheres, you would want the top one. Very simply put, you just go by the pressure units. And if it doesn't give you pressure, if you happen to be looking for pressure in your problem, then honestly you could use any of them that you want to. Your unit of pressure will just happen to be whichever one of these you pick, because everything else should cancel out. Alright, I have some problems that go with this. So here is, this is not our first one, just kidding. Let's see. Sorry, I moved these earlier. Right here is our first ideal gas law problem. So it says, how many moles of N2O gas would have a volume of 3.8 liters at 460 millimeters of mercury and 77 degrees Celsius. So what you're going to do with this is you are going to make a list. It's always a good place to start is to start with your list. So it says how many moles. So it starts already with my question. Moles is in. So how many moles would have a volume of 3.8 liters at 460 millimeters of mercury? Well, that's a pressure. And 77 degrees Celsius is going to be temperature. And kind of like our other gas law problems, if you've worked some others, we have to have this in Kelvin. So we add 273, and that's 350 Kelvin. Alright, so I know it's going to be an ideal gas problem because it's got the N. It's got this in here. But it seems that I'm missing something, because if I think about my equation is PV is equal to nRT. But I'm not really missing anything, because this is a constant. I can look it up. So I have 4 pieces, and I'm looking for that one. I'm good to go. So I'm going to plug in 460 millimeters of mercury times a volume of 3.8 liters equals N, which is what I'm hunting for, times my R. Okay, well, here's my list from before. I'm using millimeters of mercury, so I need the 62.41. And I'm just simply looking at it off of a list. So I've got 62.4 liters times millimeters of mercury over moles times Kelvin. And that's going to be multiplied by 350 Kelvin. I'm off the screen. There we go. Now, if you stop and think here for just a second, my Kelvins are going to cancel because I've got one in a numerator and then one in a denominator. So they're going to go away. Alright, I'm going to end up, I'll work this out mathematically just so you can see it. I'm going to end up multiplying 62.4 times 350, and that will give me N times 21,840 liters times millimeters of mercury over moles at this point. If I simplify the other side, that's 460 times 3.8, That is 1,748, and my units are mmHg times L, because neither one of those are going to cancel. Now, to solve for n, I need to divide both sides by 21,840 liters of mmHg over moles, which is going to make everything on this side cancel out. Alright, so that'll be divided by 21,840. Alright, and remember that when you divide by a fraction, it's really the same thing as flipping it and multiplying. So I'm running out of room, so I'm going to flip it and put moles on the top, and on the bottom will be liters times mmHg. Well, look, this is the same thing as saying it's over 1. So now mmHg cancels, liters cancels, and I'm going to be left with some number. If I put all that together, I get 0.0800, and my number of sig figs is going to be 2. So n is going to equal 0.080, and the only unit I have left is mole. So I have 0.080 moles of whatever gas that I had to start with, of N2O gas. Okay, our next equation that I want to look at is Dalton's law of partial pressure and Graham's law of effusion. So Dalton's law of partial pressure is going to show up right here. And my equation that will go with this, or my problem, is this one. It says a 32 milliliter sample of hydrogen is collected over water at 20 degrees Celsius, a little typo there, and 750 millimeters of mercury pressure. What's the volume of the dry gas at STP? Alright, a quick explanation for Dalton's law of partial pressure is that whenever you collect gases, it's usually done by bubbling the gas through water. I have another video of someone else's that I've added to my playlist where this is being watched that describes or shows how you collect a gas through water. But the bottom line idea is that when I collect a gas through water, it ends up being wet gas instead of dry gas. And Dalton's law of partial pressure says that the total pressure of any gas has to equal up to the pressures of all of the individual pieces that go into it. So, for example, if I have a dry gas, what it's saying is the pressure of the dry gas has to equal the pressure, added to the pressure of the water vapor that's on the gas that makes it wet, has to equal a total pressure. In this particular problem, the 32 milliliters means absolutely nothing, and the 20 degrees Celsius only tells me where I need to find the pressure of water at that particular temperature, and the problem tells me that. It says assume the partial pressure of water vapor at 20 degrees Celsius is 23.6 millimeters of mercury. It's giving me this. It's telling me the pressure of water at that temperature. And it wants to know this pressure right here, the dry gas. Well, what I'm missing is the total pressure. It's the pressure it was collected at. The 750.0 millimeters of mercury is going to be my total pressure. So very simply put, I just simply subtract 750 minus 23.6. And then, this one actually does ask for the volume of the dry gas, my bad. I don't mean for you to take it that far, so I'll modify the problem right here. I don't want you to take it as far as it says. So, 750 minus 23.6 is going to be 726.4 millimeters of mercury. And that's all that I really mean for you to find. So we'll change this. Alright, so there. Alright. Another way that this could work is it could simply, if I make up another sample problem, is they could simply give me some numbers. They could tell me that I have, I have oxygen, and I have nitrogen, and I have carbon dioxide, all mixed together in a container. What is the total pressure? And if I have some numbers, if the pressure of the oxygen is 1 atmosphere, and the pressure of the nitrogen is 2 atmospheres, and the pressure of the carbon dioxide is 3 atmospheres, then to find the total pressure, all I need to do is add. So 1 plus 2 plus 3 is going to be 6 atmospheres. This looks scarier than it actually is. It shouldn't be all that bad. The very last law that we have worked is Graham's Law of Effusion. And we've discussed in class from our notes that effusion means for a gas to escape or to diffuse through a small hole in something. This is another one that looks really ugly, but the bottom line is how it's going to work is I'm going to compare the rates of two gases. So my problem for that is going to come up right here. The problem says, under the same conditions of temperature and pressure, how many times faster will hydrogen effuse compared to carbon dioxide? Okay, so when it says hydrogen compared to CO2, I'm going to plug it into this equation I have on my paper here. The rate of A will be the first one, will be the rate of hydrogen. And then compared to carbon dioxide, so that'll be my B, the rate of B will be CO2. So I'm comparing the rate of hydrogen to the rate of carbon dioxide. Alright, now I wrote this correctly. I did flip them. I know over here it's A on top of B, but over here on the square root side it's B on top of A. So the thing that's on the bottom is going to go up top. I need to find the molar mass of CO2. Well, we've done this in class before. All we have to do is add up the masses off the periodic table. So the mass of carbon's 12, and the mass of oxygen is 16, but there's 2 of them. And then the molar mass of hydrogen is going to go on the bottom. And so hydrogen is 1, but it's 2 of them, so it'll be 1 times 2. So if we simplify here, that will be 44.0 over 2.0. Most students, when they mess it up because they forget either to take the square root after they do their division, or they forget to flip it over here. One more thing that can get you is don't forget Brinkelhoff. Remember that hydrogen has to be written as H2 when it's pure hydrogen. So if you mess this up and put just an H, that would change that to a 1. It's going to change all your numbers from that point forward. So if you end up doing the computation in your calculator, you end up with 4.69, you could say 4.7 sig figs. I don't really care here at this point. Round it to a decimal or 2 because you got all the numbers out of your own head or from the periodic table. There really was nothing given to you that was measured, so I'm not going to be a stickler about sig figs at this point. Okay. The next question says, if the carbon dioxide from the problem, it was problem 5, takes 32 seconds to effuse, how long will the hydrogen take? Okay. Part of that answer is going to come from my interpretation of this right here. If you end up with an answer that is greater than 1, what that means is that it's faster. So in terms of this, the hydrogen goes 4.69 times faster than carbon dioxide. That means the carbon dioxide goes slower. If I would end up with an answer less than 1, it means that the gas on top goes slower than the gas on the bottom. So when it's telling me that the carbon dioxide takes 32 seconds, this was my slow one. The hydrogen was faster. So if my slow one takes 32 seconds and it wants to know how long it'll take the hydrogen, I have 2 choices. I can either divide this number by 4.69 or I can multiply it by 4.69. I recommend using a little common sense. If I divide 32 by 4.69, it's going to get smaller. And if I multiply it, it's going to get larger. Well, if carbon dioxide is my slower one, it should take the biggest amount of time. So that means hydrogen should take less. And the way that I'm going to get less is by taking this road that I just circled. So I'm going to take 32 seconds and I'm going to divide it by 4.69, and that will give me an answer of 6.8 seconds. If by some reason you chose to go the other way, 32 times 4.7 or 4.69 is going to be 150. So if it takes hydrogen that much time, it's not faster, it would be slower. The only one that makes rational sense is this top one right there.